Rate of reaction, rate of reaction. So first, what is rate? So rate is defined as being a change in concentration of reactant or product over the time taken for this change to take place, over the time for the change to take place. Okay, so it's a change in concentration. So remember that we use in chemistry, we use delta, which looks like a triangle, to represent change. Yeah, like delta H, for example. So it's a change in enthalpy. So it's a change in concentration over a change in time, time taken for the change to take place. So the units are concentration, mole per decimeter cubed, over time. So time can be seconds or it could be minutes. I'm going to put seconds, but the time can vary. So the units are concentration, and it's 1 over time, so it's second to the minus 1, which is 1 over time. All right. So you need, in a reaction, to measure the rate of reaction, you need something to change. You need the concentration to change. You can monitor that with pH, like titration, for example. You need a gas, maybe a gas is produced, you can measure the amount of gas formed. You need something to change, right? So then what you do when you're doing an experiment, if, for example, we are monitoring the concentration of a reactant over time, so we keep checking the concentration of a reactant, and maybe it's shaped, comes out shaped like this, maybe. Or maybe we're measuring a product instead. So if we were measuring the concentration of a product, what would the shape be over time? No product at the beginning, 0 product, and then product is made, and then it goes flat like this. Okay? So if I want to find the rate of reaction at a certain time, so maybe at this time here, whatever that time is, okay, whatever it is, I want to find the rate of reaction, and at that concentration, just draw a line across that concentration, what is the rate of reaction? Now you need to draw a tangent. A tangent is a straight line, so you need a ruler, a straight line that touches the curve at this point. Now I'm not going to use a ruler, so my line's not going to be very good, but you need to draw a line that touches the curve at this point. So I'm going to just do it freehand, but you would use a ruler, and you make a nice big tangent. Okay, then you find the gradient of the tangent. Now to find the gradient of that line, it's a change in y, okay, so change in concentration, the change in the concentration over a change in x, a change in time, over a change in time, and that is the rate. That's how you find the rate at that point. Okay, now you can see that the rate is going to change, because if I find the rate at this point here, that point in time, then the tangent is going to be steeper, so the rate is faster. And if I find the rate at time 0, the rate at time 0, it's going to be very steep. The tangent is going to be very steep, and that's called the initial rate. And that's when the reaction is at its fastest, because there's lots of molecules, lots of collisions per second, initial rates. Okay, now if it's a product, you do exactly the same. So the initial will be a tangent at time 0, like this, and then you could find the tangent at various points, draw your triangles, and work out the gradient of the triangle. When the concentration doesn't change anymore, that is when the reaction is over and the reaction is finished. Okay, so when you're trying to find the rate of reaction, you have to do an experiment. You have to collect some data, you have to plot a graph. And then when you've plotted one graph, you plot a second graph. And you look at how rate is affected by concentration. So in the second year, rate of reaction, we just look at how concentration affects the rate. In the first year, we looked at how temperature, catalysts affect surface area, affect the rate. But in the second year, we just look at how concentration affects the rate. So we've got at that concentration, we've got the rate. At that concentration, we've got the rate. So we can plot rate versus concentration. Now, if it comes out like this, a straight line going through 0, what is the equation of a line? A straight line going through 0. So in maths, a straight line equation is y equals mx plus c, but there is no, it's going through 0, so there isn't any c. Okay, so it's y equals mx. Y is the y-axis, is rate. X is concentration. Now, concentration of a reactant, we don't know what the reactant is. I'm just going to put reactant. Remember what we use when we're representing concentration. We use square brackets, concentration of reactant, and M in maths, M represents the gradient of the line, and it still is the gradient of the line here, but we call it a small k, okay, a lowercase k, and that is called the rate constant. Not to be confused with the capital K, which is the equilibrium constant. Okay, that's equilibrium constant is a capital K, lowercase k is a rate constant, okay? And that's the gradient of the line. All right, so I work out k by finding the gradient of this line. Right, now if we increase the temperature of this reaction, we increase the temperature. Okay, what happens, we'll just write it down here. What happens to the rate of reaction when we increase the temperature? Well, we know that the rate increases. Yeah, more particles, I've got the minimum activation energy. So look at this equation here. If we increase the temperature, the rate increases. The rate increases. Okay, does the concentration of the reactant increase if you increase the temperature? No, that's the concentration at the beginning. That doesn't change. If you increase the rate constant increases. The rate constant increases. So if we increase the temperature and we do the reaction again and we increase the temperature, then this will be a steeper line at a higher temperature because K increases. The rate constant increases at a higher temperature. Okay, so that's an introduction. Now you need to practice questions, but let me give you a bit more information. Right, let's just take a general reaction. All right, if you just take A and B making whatever, all right, just call C, whatever it makes, all right? So there's something called a rate equation, all right? And the rate is called the rate equation, okay? And it takes the form rate equals K, small k. Do you remember what K stands for? It's called the rate constant. Only changes if temperature changes. And then we've got concentration of the reactant to the power X, I'm going to put, then times the concentration of the other reactant to the power Y. Okay, now this X and this Y, so let's do X first. X is called the order of reaction. Okay, and it is the power the power to which the concentration is raised in the rate equation. Okay, so if x equals 1, we would say that is a first order reaction with respect to A, whatever chemical A is. If x is 2, we say that is a second order reaction, and it's just the concentration to which the power is raised in the the power to which the concentration is raised in the rate equation. If you want the total order of reaction, okay, the total order of reaction is you just add them together, x and y. Okay, so this is showing us the rate. What's the point of the rate equation? Okay, it shows how concentration affects the rate of reaction. Okay, that's the point of it. Right, we need to show some examples. Let's have a go at some examples. So let's go. Right, let's take first, if you have a 0 order of reaction, okay, a 0 order of reaction. So if you take, that means a 0 order reaction, if you have concentration of the reactant, whatever the reactant is, against time, now it's a reactant, it's being used up, so it's just going to decrease with time, okay? But then, if it is a 0 order reaction, that means rate equals K, the reactant, to the power 0. Okay, the order is the power. Now in maths, when something is to the power 0, so whatever it is to the power 0 just comes out at 1. So therefore rate equals K. So when you plot a second graph of rate versus concentration, okay, if you change the concentration, nothing happens to the rate. So the rate equals K is just a straight line like this. Okay, the rate is not affected by the concentration, and that's a 0 order reaction. If you have a first order reaction, and if you plot concentration of reactant, okay, I'm going to write it like this, concentration of reactant against time, okay, and if it'll look like a curve like this, and then when you plot the rate versus concentration graph, okay, so if it's first order, it's going to be rate equals K, concentration of reactant to the square brackets, make sure it's square brackets, to the power 1. So it's going to be a straight line like a y equals mx going through 0. Okay, the last one you could be asked about is a second order reaction. 0 order, first order, second order reaction. The last one you could be asked about. Now for the second order reaction, the rate equation is rate equals K, that's a K, reactant, and it'll be to the power 2 because it's second order. So if you plot first, you do the concentration of the reactant versus time. Now a second order is very similar in shape to a first order, but it is steeper. It will decline quicker and is steeper. And then when you plot rate versus concentration, and can you see it's like a y equals x squared, so it takes the shape like a y equals x squared, and it goes like this. Okay, there are also, you can also get half orders, fractional orders, you can get negative orders as well, but in A level you will only be asked about 0, 1 and 2 orders of reaction. Okay, so when you want to see how does concentration affect the rate of reaction, how does concentration affect the rate of reaction, you first have got to do an experiment. You have to monitor something that changes, and then you have to plot a graph. Then you've got to draw some tangents, find the gradients of the tangents, plot a second graph, and to work out how the concentration affects the rate. Okay, so it takes quite a long time. If we just go back to the first order and the second order. Now remember when I said that this one here, this is a second order, concentration of reactant versus time. It looks really similar to the first order, but it's steeper. But how can you actually tell the difference? Well, first order reactions are quite special. And if you've done physics, if you do physics, you might have come across this, okay? First order reactions have a constant half-life. So this is like radioactivity. Radioactive elements have a constant half-life. You need to know what this term means, half-life. Half-life is the time taken. Half-life is the time taken. For the concentration of a reactant, to fall to half its original value. Okay, so if we take a concentration versus time graph, so this is a concentration of a reactant against time. Now I'm sketching this, so it's not going to look super perfect because I'm sketching it. So let's say the initial concentration, okay, let's say the initial concentration was 1, okay, 1 mole per decimeter cubed. Sorry, 1 mole per decimeter cubed initial concentration. Then the time taken to halve to 0.5, that is called the half-life. I'm going to draw across, and the symbol we use for half-life is T, a half. Okay, then if we halve again, that's say 0.25, then that is the same time. Now mine's a sketch, and might not look brilliant, although it looks not too bad. That is the half-life, and they should be the same number. You should have a constant half-life. And then if you halved again, what's that, 0.125, then it will be the same half-life, and it's a constant half-life. Okay, now the common mistake that people make when they're doing exams, right, common exam makes a mistake. That's a concentration of the reactant, that's time, okay, so it goes like this, and maybe that the initial is a really weird number. Maybe it's like, the initial concentration is 0.136 concentration, okay, and you've got to work out the half-life. And then what a student will do, they'll say, oh, that's a really weird number, I'm going to start at 0.1 instead, because that's an easier number to start. You cannot do that. You have to start at the start. Whatever the number is, you have to start at the start, and then you go half of that, and then you go half again. So whatever that number is, halve it, and then half again to find out the half-life. Anyway, for first order reactions have a constant half-life, second order reactions do not, and that is how you can tell the difference between them. The last bit, this is about practicing questions. You need to practice questions on this. The last bit is how to determine the mechanism. Right, so if I give you a question, let's give you a question here. So if we have this equation, chemical equation. Okay, so 2ICl plus H2 goes to 2HCl plus I2. Got that chemical equation. And the rate equation can only be determined through experiment. And the experiment has shown it's first order with respect to ICl, first order with respect to H2, because there are ones there, we just don't bother writing them in. And in total, second order overall. Okay, so it's called the overall order. So the overall order is second order, not the total order. It's called the overall order is second order. Okay, and the question says, suggest a mechanism for this reaction. Okay, suggest a mechanism. Right, so because most reactions happen in more than one step. Very few reactions happen in one step. Okay, now the relationship, the thing you need to realize here is there's something called the rate determining step. It's sometimes abbreviated RDS. The rate determining step is the slowest step of the mechanism. So it's a bit like when you're going out with your friends. We're going to go and climb a mountain. We're going to go and climb a mountain together, and you all want to stay together because you want to be safe whilst you're climbing this mountain. So the whole group, the rate of reaction depends on the slowest step. The rate of the reaction of your group, how fast you move, depends on the slowest step, the slowest person. Okay, and also the rate of reaction depends on these. So in the slow step, I know that there is going to be one ICl and one H2, because this is called the rate determining step, the slowest step, and also the rate equation shows me what determines the rate. This determines the rate, one of them. Now if it had been squared here, I would have put 2 ICl there. Okay, but it wasn't, so I'm not going to. Okay, so then I've got to do the mechanism. So what you do here, that's the first step, the slow step. Most for A level, it's going to be 2 steps. And together, it has to add up to the overall equation. So the overall equation is 2ICl plus H2 is the overall equation. Okay, I've just copied it, the overall equation. That's the first step, and we're trying to get the overall equation, right? So straight away, I can see there's another ICl. So I'm going to have to put an ICl here, because 2 ICLs will add up together, okay? H2, that's okay. Okay, and then I look and I see, okay, well, what can I form here? So I could form one of the HCl's, could be a product, and HI. Okay, so HCl and HI, but there's no HI, so there must have to be a HI here in order to, because then cancel out. And then ICl and HI, so that's going to be another HCl and I2. So I can see when I add this up, I've got 2 ICl, H2, that cancels out, 2 HCl and I2. So those are the 2 steps of the mechanism, and they add up together to give the overall equation. Right, I'm just going to give you one more example. So here is another equation. So it's a bit like a puzzle. Here's another equation. Plus O2, okay? The rate equation is KN2O5. Okay, so the first step, the slow step, which is, it's not always the first step, quite often it is. The slow step, the rate determining step, there is one N2O5. Okay, then there's going to be another step, and it's going to add up left and right to give you the overall equation. Okay, straight away I can see I'm going to need another N2O5 in the second step, so that's a 2, N2O5 in the second step. Okay, I can see I'm making NO2, so I'm going to go NO2, and what's left over? NO3. There isn't any NO3, so NO3 must be here so that it can cancel out left and right. Then there's going to be 3 NO2, because it has to be 4 NO2 in total, and O2. So just check, does that work? There are 8 oxygens, 6 oxygens, 8 oxygens, 2 N2O5, 4 NO2 plus O2, NO3 cancels out. Those are the 2 steps in the mechanism. There are other answers it can be as well.